Hello and welcome to section 8.1.1 on solving 2x2 systems of equations. First, let's talk about some basic ideas. What do we mean by a 2x2 system of linear equations? First of all, let's talk about what a linear equation is. Now, this probably is something you know for sure by now, but a linear equation is of this form. So the x and the y are both to the first degree. So if I look at this picture right here, you can see that this line right here is a positive slope. This line right here is a zero slope. So you could see equations written in this y is equal to mx plus b form, but you could also see a linear equation like a horizontal line doesn't follow that form. It looks like this. Or you could even have a vertical line, which would be an x equation. But the basic idea that your x and your y, or your x or your y, are both going to be to the first power. That makes them linear equations. Now, a system of equation is drawn as a lineup of the two equations here if it's a 2x2 system. This curly bracket here actually means something. It means that you're going to solve these two equations simultaneously together and ensuring along the way that your solution is a solution to both of those equations. So we're going to learn how to do that algebraically. So we would call such a system a 2x2 system of linear equations. This 2 means two equations. This 2 means two variables, in this case x and y. So this point right here in this graph, 2, 3, should satisfy both of these equations if you have the first case of one solution. One solution means you have one point where the two lines are going to cross. So if I substitute the point x2 and y3 into that equation here, I get 3 is equal to 2 times 2, which is 4, minus 1, which is 3. So that's a true statement. So this point 2, 3 satisfies this first equation. Now, any point with the y coordinate of 3 will satisfy this equation here. So 2, 3 also satisfies this equation. So if you have two lines that cross at one point, we have one solution. The next case we're going to talk about is the case of having no solutions. So if you look at this picture here, you can see that these two lines are never going to touch. They're parallel lines. And if you recall, parallel lines have equal slopes. So these two lines right here are parallel, and we can tell because they both have a slope of 1/2. These are not these lines. I'm just showing you an example of what two linear equations that are parallel might look like. Notice that the y-intercepts are different. Okay, so because if they were the same, then you would have two lines that were exactly the same and they would be graphed right on top of each other. So that's a different case. So the case of no solutions is the case where you have parallel lines. So those lines have the same slope but different y-intercepts. So you will not be able to find a coordinate pair, x, y, that will satisfy both of those equations simultaneously. The third and final case that we might encounter is the case where you have infinitely many solutions. And that is the case that you get when you have two lines that appear to be different, but once you reduce them and solve the system, you find out that they actually reduce to the same linear equation. So let's look at that for a minute. So these are two linear equations that at first glance appear to be different lines, but you can find a number that you can multiply each term by and reduce it to the numbers in the other equation. So for instance, in this set here, this system, if I multiplied through each of these three terms by 3/2, I would get 3x minus 6y is equal to 9, which is actually the same equation as this. Sometimes you'll see the graph showing that there's a little other line underneath, so they might be in two different colors or drawn like that. So when you have infinitely many solutions, we're going to find out how to determine this algebraically. That means you actually have the same line. Okay, so now we're going to solve this first system using the substitution method. So the substitution method means that you want to take one of the equations and write it in terms of a variable without a coefficient in front. So the easiest thing I can see to do here is to say y is equal to negative 2x plus 8. All right, so then I have an expression negative 2x plus 8. Then I would go ahead and substitute into my second equation here wherever I have a y. So I have 4x minus 4 times negative 2x plus 8 is equal to negative 8. So if I simplify that equation, I'll get 4x plus 8x minus 32 is equal to negative 8, or 12x. If I add 32 to the other side, I'll get 24, and then I divide both sides by 12, I'll get x is equal to 2. Okay, so that gives me my x coordinate. Now, since this is a solution that we're looking for that satisfies both equations, I can use either equation to find what the y coordinate is when x is 2. So I'm going to go ahead and use this one here because it's already solved for y. So I can just plug in 2 for x. So I'll get y is equal to negative 4 plus 8, which is 4. So that gives me one solution, which means these two linear equations intersect at one point, and that point will be 2, 4. All right, so we've already determined by plugging the x is equal to 2 into the first equation that this one is satisfied. But let's go ahead and check the other equation just to verify to ourselves that the point 2, 4 is also a solution to the second equation. So I've got 4 times 2 minus 4 times 4, we believe should be negative 8. So this is 8 minus 16. So this is negative 8 is equal to negative 8. So we verified that the point 2, 4 satisfies both equations. So we've solved this system of equations. All right, let's try another example here. So in this example, I'm going to start by solving one of these equations for either an x or a y. Here's an x by itself, so the easiest way I see, and it doesn't matter, you're going to end up with the same result. I'm going to solve for x here. X is equal to 2y plus 5. All right, now I'm going to take 2y plus 5, and I'm going to substitute it in for x up here. Wherever I have an x, I'm going to put in 2y plus 5. So let me just move down here. So I've got negative 2 times 2y plus 5 plus 4y equals negative 4. Distributing negative 4y minus 10 plus 4y is equal to negative 4. So that's negative 10. This is going to cross out. Negative 10 is equal to negative 4. Okay, so that is false. So if you end up with a false statement, then you have no solution, which indicates these two lines are actually parallel lines and they will not cross, even though sometimes it's not obvious before you start. So when you get a false statement, you're going to make a conclusion that there's no solution. These lines do not intersect. So I've got this next example, and I'm going to solve one of these equations for a single variable and use the substitution method. So let's use the first equation Remember, it doesn't matter which one you start with, and it doesn't matter which variable you solve for, so let's just solve for x. So I'm going to move the 2y over to the other side and divide by 2. So x is equal to negative y minus 3. All right, now using the other equation, I'm going to replace x, which is right here, with negative y minus 3. So I'll have negative 3 times negative y minus 3 minus 3y equals 9. So that's 3y plus 9 minus 3y equals 9. Well, these two are going to cancel out. So we have 9 equals 9. All right, so this, sometimes we call this an identity, and what that means is that it's always true. All right, so when you have an identity, that means you have infinitely many solutions. All right, so if you have infinitely many solutions, that means that any point that satisfies the first equation will also satisfy the second equation. So graphically, that's the case where your lines are actually lying right on top of each other, and one is in just a different form. But if you figured out what to multiply it with, you would be able to reduce it to the same numbers as the other equation. So when that happens, any point that you can figure out that is a solution to one of the equations automatically is going to be a solution to the other equation. All right, so in that case, we have infinitely many solutions. Now let's talk about some vocabulary words that are used in the study of systems of equation. So if you have an inconsistent system, that means you have no solution. So let's go back and label our problem that had no solution. So this problem is inconsistent. I should say this system is inconsistent. Then the other possibility is that you have a consistent system, and that means there is either one solution or infinitely many solutions. So the case where we have one solution, we call that independent. And the case where we have infinitely many solutions, we call that dependent. So let's go back and label our consistent independent case and our consistent dependent case. So here is our problem where we ended up with 1 point as our solution. So this would be labeled consistent independent. And here is our case where we had infinitely many solutions. So this case would be labeled a consistent dependent system. Right now you're probably wondering why we need all these fancy words to describe a fairly basic idea. Well, just think about it this way. We're starting out with the most simple problems, but a lot of studies involving systems of equations have multitudes of variables, and they're used for many different things. So we have this vocabulary which is used more for more advanced studies of systems of equations, but we learn about what these words mean starting with your most basic problems. Okay, there's another method that we use for solving systems of equations, and it's called the elimination method. Note that the instructions in the online homework sometimes call this method solving using the addition method, but its real name is the elimination method. So this theorem 8.1 here gives you 3 steps that we can use to simplify our system of equations to an equivalent system, and they allow us to solve the system using the elimination method. All right, so you can interchange the position of any of the 2 equations. That one's pretty obvious. It would still be the same 2 equations, regardless of which one was listed first or second. you can replace an equation with a non-zero multiple of itself. Basically, what this one is saying is that if you multiply each of the terms in an equation by the same number, you're just getting an equivalent version of the same line. And the last one is not so obvious, but it does allow you to have an equivalent system. You're going to still get the same solution. And this one says you can replace one of the equations with itself plus a non-zero multiple of one of the other equations. All right, so believe it or not, that's a valid maneuver which still allows you to get the same solution. So we're going to use the elimination method. And so we want to make sure that we do learn how to use the elimination method. This is the precursor for learning how to solve systems of equations using matrices. I'm not sure whether we're going to get that far during this COVID semester, but that's where this is leading. So I want to pick a starting point. I want to choose to either eliminate the x variables in these equations or eliminate the y variables in these equations. So let's just arbitrarily say I'm going to choose to eliminate the x variables in these equations. So what I'm going to do is I'm going to choose to multiply the x terms in, let's just say, the top equation by some fraction. In this case, it's going to have to be a fraction to cause that 3 right here to be a positive 2, so that when I add 2x and negative 2x together, these two terms are going to cancel each other out. So this is why some people are tempted to call this the addition method, because basically we're going to try to add these two equations together and drop one of these variables out. So we'll have an equation left to solve that's only in one of the variables. All right. So the way that you do this is you're looking for, what do I need to multiply this negative 3 by to turn it into a 2? So it needs a 2, and it needs that negative 3 to cancel out. So that's how you can see that if you cross out the negative 3's, you'll be left with the 2. So you need to multiply this entire equation here by negative 2/3 in order to get that to be a 2x in the first position. So we usually put this arrow here, and then we write negative 2/3 above the arrow to signify that I'm multiplying each term by negative 2/3. So we already said the first term is now going to be a 2x. Now if I multiply negative 5 by negative 2/3, I'm going to get 10/3. So that's going to be my y coefficient. And then there's one more number, the 1. If I multiply 1, I'm talking about this one here, by negative 2/3, I should get negative 2/3. So let's just review what we did. So I figured out I'm going to try to match up the coefficients of these x terms right here to be equal and opposite so that I can add this equation to this, and these two terms will drop out. So if I multiply every single one of these terms by the same number, I'm following the second rule here. Then I should have an equation that is just a different form, but it's actually the same line. So negative 2/3 times negative 3x is 2x. Negative 2/3 times negative 5y is 10/3 y. And negative 2/3 times 1 is negative 2/3. All right, now I'm not going to do anything to the second equation. I'm just going to write it right here, like that. All right, now I'm going to add the two equations together, and that's going to cause those first two terms to drop out. 2x minus 2x drops it out. So then in the second, in the y spot, I'm just writing a little fraction problem over here. I've got 10 thirds minus 3. 3 over 1 is 3. I need common denominators, so I'm going to multiply by 3 over 3. So that's 10 thirds minus 9 thirds is 1 third. Now I'm going to do the same thing for the last term. I've got negative 2 thirds plus 1. 1 is just 1 over 1. Getting a common denominator here, I've got negative 2 thirds plus 3 thirds is 1 third. So 1 third over here. Now you can see that if you divide by 1 third, you're going to get y is equal to 1. All right, so we found that y is equal to 1. Now you can substitute that 1 into either of the equations to solve for x. So let's go ahead and use the bottom one. Doesn't matter which one you use. I'm substituting 1 in for y, so I'm going to get negative 2x minus 3 is equal to 1. Negative 2x is equal to 4. X is equal to negative 2. So this looks like we have one solution. So one solution means that it's a consistent, independent system of equations, and my solution is the point negative 2, 1, and these lines cross at the intersection 1 point. So here's another problem. So we're going to solve this using the elimination method, and what we do is we multiply one of the equations by a constant so that when we add the two equations together, one of the variables, either the x or the y, will drop out and we'll have an equation to solve with only one variable. So I'm just arbitrarily going to choose the bottom equation to work on, and I'm going to get the x terms to cancel out this time. So that means I need to figure out what I need to multiply negative 4 by to turn it into a positive 3, so that this will say 3x here, so that when I add negative 3x and 3x together, these two terms drop out. So if I look down here, I want to end up with a 3, and I want the negative 4 to cancel. So I'm going to have to multiply this second equation by negative 3 over 4. And I'm going to get a new equation. Let me just move this over, and I'm going to write it down. We already know that the first term will be 3x because we figured that out already. Now you can see here that this is the same coefficient, so I would have to multiply that one by the same negative 3x here. So you'll get 3y, and then if I multiply the 0 by negative 3/4, you're still going to have 0. So I've transformed that equation. Now I bring the other one over here, so I've just got negative 3x minus 3y is equal to negative 3. All right, so now we go ahead and add these two equations together. So the first two terms, the x terms, drop out because we fixed it that way. Now these two are also going to drop out in this system. So we've got a 0 here on the left-hand side, and we've got on the right-hand side negative 3 plus 0. So that's equal to negative 3. All right, that looks like a false statement right there. So that indicates we have no solution. So there's no solution for this system of equations, and we call that an inconsistent system of equations. All right, so this is our next problem here. We're going to solve using elimination. So I'm going to go ahead and try to eliminate the x's once again. So if we're going to do that, I'm going to try to get a negative 5 here. So this has to be a negative right here. So I'm going to figure out what I need to multiply negative 4 by to turn it into a negative 5. So that means I want a 5 on the top, and I want a 4 on the bottom. All right, and that will give me, if these 4's cross out, that will give me a negative 5. So I'm going to multiply the second equation by 5 over 4. So the first term is going to be negative 5x, and then that negative 4 coefficient is the same here. So we're going to have negative 5y as well. And then that negative 8 here on the end, if we multiply it by 5/4, let's cancel out the 4 and make the negative 8 and negative 2, so that's negative 10. So on the right here, I've got negative 10. All right, then on the top, I've got 5x plus 5y is equal to 10. All right, so now if I add these two equations together, I'm going to get 0, 0. So that's a 0 on the right, and a 0 on the right. So we've got 0 is equal to 0. Well, that's an identity. That's an identity, so that means we have infinitely many solutions. But we're not going to stop right there. What you do when you have infinitely many solutions, many times you report your point in terms of one variable. And what we mean by that is we call it a parametric solution. So parametric form means if you just pick any x, we want to figure out how to write an expression for the y in terms of x. So either of the equations will give it to you. So let's just look at the first equation that says 5x plus 5y is equal to 10. I'm going to solve that for y in terms of x. 5y is equal to negative 5x plus 10. Dividing everything by 5, I have y is equal to negative x plus 2. All right, so that's what I'm going to write there on that line. So let's pull this all together. So if you have infinitely many solutions, we know that we do when you have an identity that you wind up with when you solve this system. All right, if you have infinitely many solutions, we call that a consistent dependent system of equations. All right, so the way that we report our answer in parametric form is that we solve for one variable in terms of the other. So generally you would start by saying x is equal to x, whatever x you've got, and then you solve for y in terms of x, and you replace the y in your point with this expression here. Okay, a lot of times also, let me just point out that you're not going to see it called x there, you'll see it called a dummy variable. So it's very common to see it called t in parametric form. So let's just use the letter t when we write our point, our solution in parametric form. All right, the last thing we're going to do is try a word problem. So the coin problem is a standard systems of equations problem. So let's figure out how to write a system of equation that represents this word problem here. So it says, Judy has 27 coins in a jar. There are only dimes and quarters. The total value of all the coins is $4.50. How many, this should say many, dimes and quarters does Judy have? All right, so let's look at the first sentence. It says Judy has 27 coins in her jar. All right, we also know that there are only dimes and quarters. So let's say D represents dimes and Q represents quarters. So D would be the number of dimes and Q would be the number of quarters. So the first equation says if there's 27 coins in a jar, so D plus Q, the number of dimes, plus the number of quarters then would have to be 27. All right, there's one equation. Now it also says here that the total value of all the coins is $4.50. All right, we don't want to mix units here. We don't want dollars and cents mixed together. So it makes most sense to work in terms of cents because a dime is 10 cents and a quarter is 25 cents. So let's work in cents. So $4.50 is the same thing as 450 cents. All right, so we've got the number of dimes times the value of a dime, which is 10 cents, plus the number of quarters times the value of a quarter, which is 25 cents, must add up to 450 cents, according to what it says. So now let's just use the substitution method. Since these two variables don't have coefficients, it'll be pretty straightforward. So let's solve for D in terms of Q. So that means if D plus Q is equal to 27, then D is equal to 27 minus Q. All right, so if D is 27 minus Q, then I go to the second equation, and wherever I have a D, I'm going to put in 27 minus Q. So I have 10 times 27 minus Q plus 25Q is equal to 450. So I have 10 times 27, well that would be 270 minus 10Q plus 25Q is equal to 450. So that's 270 plus 15Q is equal to 450. So if I subtract 270, I'll have 15Q is equal to 180. Now let's divide by 15. So that means Q is equal to 12. All right, so that's my number of quarters. All right, so now if I have 12 quarters, then if I go back up to my original two equations up here, if Q is 12, then D is 27 minus 12. So that's 15, right? So that means the number of dimes is 15. And I've solved my problem. So I have 12 quarters and 15 dimes. That adds up to 27 coins. And the value of 12 quarters and 15 dimes is $4.50. So that's enough information to solve assignment 8.1.1 problems. So give those a try. And if you have any questions, let me know.